Hello again folks, and welcome to another Biomechanics screencast, and this particular Biomechanics screencast is going to be focusing on spin diagrams, so use of the Magnus Force and the airflow diagrams that relate to this. It will also cover the other diagrams such as free body diagrams, flight path diagrams and resultant force diagrams for the various types of spin. If you haven't seen the screencast on the Magnus effect, I seriously suggest that you watch that one first and then come back to this one so you understand the principles. Alright, basically, as discussed in the last screencast, we talked about topspin and the Magnus Force. So my main example was about topspin. So if we're hitting a ball outside the centre of mass with an eccentric force, we're creating topspin. The upper surface, remember we need to think about the surface of the projectile in two halves. So the upper surface, or the top half, rotating towards the oncoming airflow, that is going to reduce air velocity and creating high pressure. And the lower surface, if we're doing topspin, remember, will rotate in the same direction as the airflow, increasing air velocity, so air will speed up underneath the ball and it creates a low pressure zone. Therefore, this is creating the pressure gradient between the top half and the bottom half of the projectile, and we have this issue of the Magnus Force being created to pull that ball gradually downwards as it's being hit. Okay, so again, if you're not happy with that stuff, pop back to the original screencast on Magnus Force and then come back to speak about the diagrams. Whenever you're doing any sort of diagrams, always remember the key point: if velocity increases, pressure reduces or decreases. So the main bulk of this screencast now will show you how to draw the airflow diagrams for spin, and then I'll show how that alters the free body diagrams, flight path diagrams and resultant force diagrams where necessary. So we'll start with topspin, work our way through, followed by backspin, and then I'll start to talk about hooks and slices and how they are slightly different. Alright, so if you remember your lift diagrams with the Bernoulli effect, the airflow diagrams are always the same in terms of you've got to put the air resistance lines on these. So let's look at topspin to begin with. So always draw a direction of travel. In this sense, topspin, we're going to hit the ball to the right. Make sure you draw the diagram nice and big and make sure your lines are clear. Also, don't spend a long time designing your tennis ball. A circle will be fine. I've got an image of the tennis ball because it's easy for me to grab, but a circle is the easiest option here because it's just a tennis ball. Okay, you haven't got enough time in the exam to worry about that. So once you've done your direction of travel line, you need to put what we call rotation lines into the projectile. The rotation lines tell us which way the ball is spinning. So because my black arrows are spinning in this particular direction, and I've got a direction of travel line, it tells me I've applied topspin. Okay, then you can start with either of the airflow lines. So to begin with, if we're doing topspin, air over the top will be going against the spin. So remember, with top half of the ball and bottom half of the ball, you're thinking about that in terms of pressure gradients. So the air over the top will have a big gap in between your three air resistance lines to show that it is moving slowly. As I mentioned before, a minimum of 3 air resistance lines. 4 is probably best when you're drawing those, but do make sure you've got a big gap in between each line, because when you hit a ball with topspin, that air is moving much slower and you need to show that. Don't forget to put arrowheads on the end of your air resistance line. The air resistance lines always go against the direction of travel, so you can see they're opposite. The blue lines are opposite to my white direction of travel line. And then of course you just need to do the underneath of the ball, the lower surface, and of course air resistance is going with the spin at this point. So these lines will be nice and tight together, as tight as you can make them. Again, minimum 3. 4's great, but I just haven't got room on this screen. Again, make sure you've got your arrowheads on. Now to finish the diagram, once you've done this for topspin, there are a couple of things to add in. You've got to draw a line from the centre of mass down. probably about the length I've given it there, and label that with an M. That's the Magnus Force. So you've just labelled the Magnus Force on your diagram. And then we need to talk about the pressures with the two lines. So above the tennis ball, those arrows are bigger gaps, so therefore it has low velocity and high pressure. You must label that to gain marks. And underneath the tennis ball with topspin, there is high velocity air resistance, so it's travelling with the spin and therefore creating low pressure. So you now have a complete diagram that you will be required for all the marks in your exam, so don't lose that image. Okay, so that's the airflow diagram for spin, for projectiles, for topspin. We're now going to show how the Magnus effect affects free body diagrams for topspin projectiles. So again, free body diagram, direction of travel, put in, draw your circle for a tennis ball, nice and big, make it clear. If we're doing free body, start at the centre of mass. The ball has been hit mid-flight, so there's a degree of air resistance, but generally speaking, the weight of that tennis ball is still greater than air resistance, so therefore there'll be a slightly longer weight line. However, we've now got to talk about the Magnus effect. So when you write the weight at the bottom with a W, you must put plus M, because the ball is having an extra Magnus effect, bringing the ball downwards. So on your free body diagram, for a top spin shot on a projectile, you must add the M with your weight. And don't forget to then write an equation. Weight plus Magnus force, so W plus M, is greater than air resistance or greater than AR. That's always worth writing in case the examiner can't make out your lines. Now, because we've got the Magnus force present for a topspin shot, it is always a non-parabolic flight path. So that's always worth remembering when you're writing the free body diagram too. If the Magnus force wasn't there, it will be a parabolic flight path. But because of the spin, it's deviating. So therefore a non-parabolic flight path is occurring. Okay, so again, still sticking with topspin, how do we put the Magnus force into a resultant force or parallelogram of force diagram? So here it is. So if you remember with your resultant force diagrams or parallelogram diagrams, same principles apply. Direction of travel needs to be put in. Nice big tennis ball. Start off with a free body diagram like we've just done. So air resistance from the centre of mass, weight from the centre of mass. But now we've got the Magnus force, so we've got to add the plus M. And then the rest is the same as a resultant force diagram. So draw your orange lines to make a parallelogram. Your white line or a line from the centre of mass as a diagonal and label resultant force. Just don't forget to put the W plus M on this resultant force diagram because it's showing that this is part of topspin. Otherwise, it would be a shot put if you miss the M off. It'd be the same thing as a parabolic flight path. Okay, so that's a complete resultant force diagram. Remember, they are separate diagrams to free body diagrams. Don't ever draw one on top of the other. Make sure you have two separate. Finally, for the topspin diagrams, diagram number 4 is the flight path diagram. Now again, if we were throwing a tennis ball without any spin, no spin at all, it should in theory give us a parabolic flight path, because essentially it's the same as a shot. It's a circular sphere. It should give us that. But because we've got this Magnus effect, what's happening to the flight path is that it becomes non-parabolic. And if you've played tennis or played table tennis, probably the same thing, if you hit a ball with topspin, the ball will dip very quickly. And that's the advantage of using it. It confuses an opponent. So when you're drawing the flight path diagram, it needs to look like this. So it's hit as if it's going to curve and it dips very quickly. Remember to draw the arrow on your flight path diagram, or at least an arrow underneath for the direction of travel. And again, this is what the flight path diagram should look like. So you've got these 4 sets of diagrams for the spin aspects. You just then need to repeat them for the different types of spin. So let's go back to the start. We'll start again with the airflow diagram. But this time we'll look at backspin. So direction of travel line in first, so I'm going to hit the ball to the right of the screen. And this time I'm going to place an eccentric force underneath the bottom of the ball. So I'm almost chopping the ball underneath. And what that should do to the rotation lines is alter them the other way. So it's the complete reverse of topspin with the arrows. The arrows go a different direction. You must have those rotation arrows in on your tennis ball diagram. Now, thinking logically, the air over the top that the ball meets, remember we're talking about the top half of the ball, bottom half of the ball, the air over the top is now going with the spin that I've applied. So the air resistance lines with the arrowheads at the end will be going with the spin, and so these lines now need to be the tight lines, and therefore velocity of air on the top is much greater. But the bottom half of the ball is going against the spin. So the bottom half air resistance lines need to have the longer gaps in between them. Remember, at least 3 lines for each of those, if not 4. And finally, to add to this diagram, the Magnus effect is travelling in a different direction this time. It's taking the ball slightly upwards. Remember to label that as M. Remember to draw that from the centre of mass upwards. To complete your diagram, remember, we need to talk velocity and pressure. So all we've got to do is add the statements in. High velocity, so faster airspeed on the top, and low pressure is above the tennis ball, and low velocity and high pressure is below the tennis ball. When you write those in, they must be next to the arrows, or above and below in the correct order, or with the correct part of the surface. And that is a complete backspin air flow diagram. So let's move on to the free body diagram. Same principles. Draw yourself a tennis ball, draw the direction of travel in, air resistance coming away from the centre of mass, because you imagine you've just hit the ball, it's mid-flight. This time, however, because we've got Magnus working in an opposite direction, we can label this weight minus Magnus. There is an alternative to this. You could also draw a line upwards from the centre of mass and label that M. That would also work. So either would work here, as it's explaining that the Magnus effect is in operation as this ball is spinning. Once again, because we've got the Magnus force present, it has to be a non-parabolic flight path. If we then apply that to the resultant force diagram, pretty similar. Direction of travel, draw yourself a tennis ball, free body diagram as we've just done. So remember to write the minus Magnus force because the Magnus force is lifting it upwards. Draw yourself the parallelogram and the diagonal line. Okay? And so the resultant force will be in the corner, as is that. Okay, finally the flight path diagram is slightly different for backspin than the topspin one. Again, draw yourself a tennis ball. This time, if I hit underneath a ball, what it will do is the ball will lengthen its flight path because it's generating a Magnus force upwards, so it's slowly lifting the ball as it's being hit with spin. And so it becomes longer in the air. It also becomes a slower ball as you hit it. Therefore, it is a non-parabolic flight path because you've got spin, and that should say backspin, apologies. The backspin shot makes a ball lengthen its flight path, so make sure you've got that right. All right. Now the final 2 diagrams relate to hooks and slices. And when I explain this to students, they first of all don't know what a hook is. So the best way I can describe a hook is if you're playing golf and you hit the ball, so you're looking down on the ball from the golf tee, and you hit the ball slightly one side of the ball, so you're hitting it on the right side of the ball will start to bend to the left. Okay, so imagine you're looking at the tennis ball top down, bird's eye view. You hit the ball on the right hand side of the ball and it will rotate to the left. And that is a hook shot, often used by footballers or golfers mainly, but also things like table tennis and tennis also use hook shots. If we're drawing an airflow diagram to explain this, you've got to imagine you're looking at the tennis ball top down, bird's eye point of view. So you draw yourself a circle like I have done here. The critical thing with this diagram is the direction of travel line. The direction of travel line now is going upwards because I'm looking at it top down. So as that ball is travelling, I've hit the ball with an eccentric force on the right hand side of the ball. And that means the ball is starting to rotate to its left, hence the black rotation lines. Again, you must have those rotation lines correctly done. So these are the rotation lines for hooks. As the air meets the ball, looking top down, the right hand half of the ball is now going against airflow. So the right hand air resistance lines are going to have the big gaps because airflow is going slowly at this side of the ball. And that means on the left hand side of the ball, air resistance is going with the spin or rotation of the ball. And so there'll be tighter lines, tighter air resistance lines on the left hand side of the ball. Don't forget to draw your arrowheads against the direction of travel. So my white direction of travel line is going up, the arrowheads are going the opposite direction. That's really important. Two things left to do then on this diagram. You can then draw in the Magnus Force, which pulls the ball to the left. So I've hit it on the right hand side, top down, and the ball starts to spin to the left. And finally, we then need to talk about pressure and velocity. So clearly the blue lines have low velocity but high pressure, and the red lines have high velocity but low pressure. So again, this shot is used by golfers, footballers, table tennis and tennis players. The only other thing you need to understand about hook shots is that you will be asked to draw a flight path diagram for these. You don't often see resultant force diagrams or free body diagrams for hook shots because it's hard to draw it being top down. And so therefore, you'll need to concern yourself with the flight path diagram. So again, make sure you've got your direction of travel line right. You're looking at it top down. Draw your tennis ball, or whatever ball it is, golf ball, direction of travel is going upwards. And so clearly the ball is going to go to the left. So all we need to do is a nice arrow bending to the left. And the statement is that the Magnus Force being present gives you a non-parabolic flight path and it rotates the ball to the left. So that is the flight path diagram for a hook. A slice is pretty much the opposite to a hook. So I'm going to hit the ball, if I'm looking at it top down, I hit the ball on the left hand side. I place my eccentric force on the left, and that means the ball starts to spin to the right. The critical thing to understand for hooks and slices is that the answers only relate to right-handed or right-footed players. So if you're left-handed, get your head round that. So right-handed players will slice by applying the eccentric force to the left-hand side of the ball. Okay, so be careful with that. So draw yourself a nice round ball. Again, direction of travel is going to be upwards because you're looking at top down. The rotation lines will be the reverse of the hook, so they're rotating to the right this time. So make sure you've got those in, and therefore you just add your air resistance lines. So the blue lines this time are going against the rotation on the left hand side, and the faster airflow is going with the rotation on the right half of the ball. So the right half should be tighter lines, the left half should be gapped lines. Remember your arrowheads when you're drawing the diagram. Your Magnus effect will therefore pull the ball to the right because that's the direction the spin will be going in. So remember to label that as M from the centre of mass. And finally, talk about your pressure and air velocity. So on the left, we've got low velocity but high pressure. And on the right half of the ball here, we've got high velocity and low pressure. And again, that is your completed exam answer diagram for an air flow diagram for slice. And finally, to finish this screencast, sorry it's been a bit long this one, the slice flight path diagram is exactly the same as the hook one, except the curved line is going to go to the right instead of the left. So remember that direction of travel line when you're drawing this. Make your ball nice and easy, curved arrow to the right. Once again, as the Magnus Force is present, a non-parabolic flight path occurs. Apologies, that should say the slice shot underneath. So the slice shot makes the ball rotate to the right. Okay, thanks for watching this screencast. There's a lot of diagrams here. You need to be able to draw the diagrams large, clear, with everything that I've asked for on that diagram. You will lose marks, individual marks, for missing anything that I haven't got on those diagrams. So please make sure you go over them very clearly and you've got good notes or good drawings in your notes for when you do your revision. As I say, thanks for watching, and if you need any more help with biomechanics or any other aspects of A-level PE, please head to the ispeakPE channel on YouTube.